Oke, selamat pagi semuanya. Kita akan melanjutkan perkuliahan. Jadi kali ini perkuliahannya adalah lanjutan dari yang kemarin ya, tentang lebih jauh lagi di microprocessor. Nah, katanya sekarang dengan microprocessor 8085. Okay, about the architecture of 8085, yeah. So this one is the 8085. Intel 8085 has a 8-bit and most microprocessor is available, which is it has 40 pins. Okay, the pins will be described as following. First thing first, about the power. It has 5 DC volt power, so the clock speed used in this microprocessor is about 3 megahertz. Okay, so it has a general purpose 8-bit microprocessor that we already discussed, B, D, and so on and so forth. Yeah, the main function of 8085 is R register section, arithmetic and logic unit, LU, timing and control section, interrupt control, and serial output input. Yeah. Okay. This is we have a BDH general purpose register, which is it can be used in pair, sorry. So B, C can be used together in the form of 16-bit. So each of them is 8-bit wide. Yeah. So D and E also can be used as a pair, 16-bit. Yeah. Which is each of them is 8-bit. It is same as H and L registers. So each of them is 16S and data address. Okay. So whenever the latch will be here, the data section here will form as address. So this one will form as a less significant bit. This one is being formed as a higher nibble or more significant bit. So this is the lower nibble. This is the higher nibble. So we have a timing and control part here, which is we have a clock generator, X1, X2, and then clock out, ready, and then control status, DMA, and reset. So here we have an accumulator, which is we sometimes call it as a register A, and temporary register. Yeah, temporary register is used to form the arithmetic logic unit. This is just like a buffer that used for doing the arithmetic. Yeah, momentarily doing the arithmetic. And usually if you do the arithmetic, for example, addition, register A will be added with register B, for an example. And then temporary register will be hold the value in the register A. So, and then after that, the result of the arithmetic will be stored in the register A. Whatever you do the logic and arithmetic thing, the result will be stored in the register A. So it is why temporarily register and accumulator should be used in pair. So the next one is the flex and flip-flop. So flex and flip-flop, it is indicate the process that you were executed. Okay. So for example, the result of the arithmetic is all zero. So the flag zeros will be on. For example, you have resulted in arithmetic operation carry. So the flag carry will be on, and so on and so forth. Yeah. And then in the outside area, we have interrupt control. Interrupt control is for the amount rank. Yeah, we call it as a rank. Yeah, because interrupt is doing something which is related with the rank, related with the level of the activities. If it is high level activities, then the interrupt control will be override ongoing activities, and then after that the ongoing activities will be halt for the moment. So how to do the halt and the allowance process of another control or another activities, it is by using we call it as a pop and push stack. So the previous or ongoing activities will be stored momentarily in the stack, and then after that, we do the high rank level, yeah, of importance, of course. And then after that, after the interrupt already done, then the previous session that being stored in the stack will be come out again. Okay, and then we have a serial input output control, which is for so remember the sign flag. So the sign flag have a S, which is sign flag. I mean the flags, yeah, flag activities, which is located in here. Flag. We have sign flag. Sign flag is for indicate the result of the arithmetic logic unit is positive or negative. Yeah. This is the unity of the result, unity of the what we call as a data, whether data originally is the sign value or not. So whenever it is sign value, then we use the idea of sign flag to indicate the degree of the data. But if it is not sign flag, then we can neglect the activities of the sign flag. And then after that, we have a zero flag, which is indicate whether data all is zero. And then we have a auxiliary carry flag, which is indicate whether the D4 of the result, yeah, in the arithmetic logic unit is from the carry of D3. So D4 the result of the arithmetic logic unit, whether it is the carry of D3 or not. Okay, the half carry, the half nibble. Maybe we can say that. Okay, P is parity. It is active. It is 1 if it is even parity. If it is 0, then it will be indicated that the result is odd parity. So finally, we have a carry flag, which is indicate that D8, yeah, virtually block D8 is resulted from the carry of D7. It is. And then we have an instruction register and control signal. We will explain the block diagram one by one. And then instruction registers. So as I said in previously, CPU fetch the instruction from the memory of its execution. So the instruction can be 1 till 3 byte long. So the first byte contains the opcode instruction, which basically specifies the nature of operation to be performed, indicating the length of the instruction. The first byte, we call it as a opcode of the instruction. Transferred 8-bit instruction register through the internal bus of CPU. So becomes available at the instruction decoder. The decoder decodes the opcode and direct the control unit to produce the necessary control signal. So this is the set status signal and control signal, yeah, from the instruction register. So first thing first is the status signal, which is from the pin ALE, yeah, S1 and S0. So ALE stand for address latch enable. The address latch enable is the positive pulse that activate the external latch IC in the first machine cycle. This tells the external latch to wake up, address line incoming. The latch respond the demultiplex of address data 0 to 7 pin to A0, A7 and D0, D7. As I said previously, here the latch will be combined all the blocks. If it is operate for the address data, then latch will be combined data here and data there. Okay, so data here will be act as a less significant bit. This block will be acted as a more significant bit. So S1 and S0 is the status signal. Yeah, we can see here the status signal. If S1 and S0 is 0, 0, then operation is halt. If S1 and S0 is 0, 1, then the operation is right. If S1 is 1, S0 is 0, the operation is read. Both S1 and S0, 1, then the operation is fetch. Okay. So this is the cycle status. Yeah. R means read, WR means write, and IOM is for the input-output memory. So read here, which is the control signal S1 and S0, 1 and 0, is the active flow input. This is the signal, yeah, signal that indicate that the operation is currently read the data. When it goes slow, the microprocessor read data from either input device or memory in simple terms. So then the microprocessor takes data input by placing the data from source memory on the data bus. Okay, so write another active flow pin, which is opposite work of the previous pin. When it goes low, the data bus is being written to memory location or an input output device. This is the input output memory. So it is the status signal like S0 and S1 status signal. In fact, it can be used tandem with the S1 and S0 pin to give the idea which machine cycle is being processed. So this is quite nifty. Check out the table below here. Now, as we saw the above two pin, the data will be sourced either from memory location or an input-output device. The address of both of these locations are different. It helps distinguish between which address is being used to the source data from the input-output or the memory. So, for example, if the status is 0 here, 1, 1, so the opcode is fetch. So the control signal will be read is 0. Yeah, so the control signal should be read in 0. So you fetch the opcode. Okay. If input output M 1 and 0, it means that you read from the memory. So the read is 0. So if it is 0 and the status signal 0, 1, so you write the memory. Okay. So the control signal write. If it is input output memory 1, meaning that the active is input output S1 and S0, 1 and 0, the machine cycle input output read. So the control signal will be active flow read. Same goes on if the input output 1. So remember, when input output is being activated, it means that you read or write data to the external external memory. If it is 0, then you input or output data in internal memory. So if it is 111, yeah, it means that interrupt acknowledge. Control signal is interrupt acknowledge low. Yeah. So if it is 00, then the operation will be halt. Yeah. If and only if the interrupt is 1. Yeah. Whatever the stand here, read and write. Yeah. If interrupt is 1, then this condition will be activate. Yeah. Here is the interrupt pin. So trap reset 7.5, reset 6.5, reset 5.5 are the multiple vector interrupt for the microprocessor. The interrupt is used for transfer data from peripheral. Different programs stored in the different locations start executing once a signal given of any of these pins. However, this can be masked using code. Check out the table later on for the priority of this interrupt. If two simultaneous interrupt are received, the microprocessor execute according to the priority level. So we have a interrupt request here, another interrupt. this one above actually interrupt the normal functioning of the microprocessor. However, interrupt request here, which has the lowest priority, execute on the completion of the current program. So after the program is being fulfilled, that this interrupt will be executed. Once the interrupt signal from the INTR is acknowledged, then interrupt acknowledge signal is issued. So this is the interrupt acknowledge. It is just a signal that given out after the interrupt request is received. So this is the tabel. This is the highest priority. It is trap. Yeah. Trigger is the signal level and age. This is non-maskable because it cannot be controlled via programming. So it's used to be controlled using the hardware signal. Okay. So simply saying this trap will be active if and only if you have a signal in the pin trap. Okay. So the 7.5, reset 7.5, reset 6.5, and so on and so forth. It is the maskable interrupt. So interrupt priority is second, three, fourth, and then the lowest one is the interrupt request level. Okay. This is the clock signal. Yeah, I already explained about that clock signal in previous slide. We have reset in, bar on top on the pin indicate this is the active flow. I already mentioned it before. Mean that it is active when given the zero or low input, ground input. When it is high, then the activities inside of the reset will be off. The functioning is the reset microprocessor. So program counter, which is increase the program execute, set 0, a fresh start. So low input remove, the microprocessor begin executing instruction from very first condition, which is 0 hexa trace. So reset out is the signal that used in indicate that microprocessor being reset, and the other one reset external peripheral for the CPU. So when the CPU being connected with the peripheral, so when reset out signal is out, then it can be used for indicator for the other peripheral to be this is the DMA, direct memory access, simply saying that DMA is used for the copy and paste the information as fast as it can. So it can be used for direct access to the other peripheral's memory without it in the previous slides. Yeah, signal control should be activate, and then you should be know the location of the memory and so on and so forth. But DMA can simplify all the process, even though the majority process is processed, but the velocity, yeah, we sometimes call it as velocity of the processing access original access memory. Okay, and we have a signal pin hold and hold acknowledge. So hold used to communicate between microprocessor control and external device. So usually external device is requesting the use of the address and data bus, suppose the shift register, and then counter appear and send signal to the hold pins. And then microprocessor say, hang on, let me finish the current machine cycle. Once microprocessor does it, it give up the control passes to the counter and then send out the acknowledge signal via hold acknowledge pin. So the hold acknowledge pin goes high when microprocessor surrenders its control to the passes in response of the HOOT call. Once HOOT request is attended to, the HOOT acknowledge pin goes low, the processor takes over the passes. This is the input output signal. We have a serial input data and serial in output data. Of course, input is for the input, yeah. Output is for the output. Input accept the serial input data transfer pin to the 7th bit of the accumulator when RIM instruction execute. RIM instruction is the instruction that used couple with the serial activities. So after pin output serial into 7th bit accumulator is on, then SIM instruction will be executed. Will be take a look at the SIM and RIM instruction in the post on the instruction set. Okay, so SIM also a signal that being coupled with the output. RIM will be mostly coupled with the input serial. Okay, I think this is the, what is it, introductory. So I will give you lecture about how supposed to be work. Yeah, and in the next lecture. So stay tuned and goodbye. God bless you.